In many ways, polynomials are the simplest functions. What would it look like for a second-order linear homogeneous ODE to have a polynomial solution? So we always talk about how derivatives have the additivity property, and so if we're talking about solutions to a differential equation, you can chunk the solution into different terms. And so if I only care about polynomial solutions, I can just consider each term of the polynomial solution independently and then think, what would it look like to have a second order linear homogeneous ODE to have a solution that looks like y equals t to the power r, or a monomial. And if I've got y equals t to the power r, I would have y prime equals r times t to the power
plus 1,
r minus 1. And then the second derivative would be
r times r minus 1 times t to the r minus 2.
There you go. And this is supposed to be my solution for a second order linear homogeneous ODE. Notice I didn't specify this has to have constant coefficients. So in general, this could be some function of t times y double prime plus some function of t times y prime plus some function of t times y. And since it's homogeneous, the right-hand side has to be equal to 0. But in general, that's what my second order linear homogeneous ODE looks like, where p, q, and r are just possibly nonlinear functions of my independent variable t. And so if I take this orange equation and I plug in the definitions now for y double prime and y prime and y, I would get some capital P of t times r minus 1 times t to the power r minus 2 plus some capital Q of t times r times t to the r minus 1 plus some capital R of t times t to the r power. This has to add up together to equal 0. And it's not just equal to 0 for some value of t, but it's supposed to be identically equal to 0 for all real number values of t, is what I mean by that equal sign. So what would it look like for the left side of the equation to be equal to 0 for all values of t? Well, it would actually be really nice if we could group the same powers of t and make all of the powers of t r, right? And so it would make sense for p of t to be like t to the 2 power, and q of t to be t to the 1 power. And capital R of t might just be a constant, because do you see how the t to the 2 is going to multiply t to the power r minus 2, and then we just get t to the r, and then every term on the left-hand side of the equation would have a factor t to the r power, and then I could give myself some constant factors to work with and tweak the values of a, b, and c so that these terms would cancel each other out no matter what r is, right? Because r is a constant as well. And so the form of the equation that would have a polynomial solution would look something like a t squared y double prime plus b t y prime plus cy equals 0. And by choosing the right values of a, b, and c, I could make this second order linear homogeneous ODE have a solution t to the r for some r power. So since this can have polynomial solutions, we gave it a name. We call this specifically the homogeneous Cauchy-Euler equations. So, exercise 1. For a given homogeneous Cauchy-Euler equation, how would we determine the general solution? There's going to be 3 cases. In this case, we're going to consider distinct real values of r. So let's write down at squared y double prime plus bt y prime plus cy equals 0. And the solution we're looking for are things like t to the r power. And we already found the first and second derivatives of this. So when I plug this in, the first term is going to become a times r minus 1 t to the r power. The second term is going to become b times r times t to the r power. And the third term is going to be c times t to the r power. And this has to be equal to 0, not just for one value of t, but I want this to be identically 0 for all real values of t. So factor out the t to the r power, and we would be left with something like this, where in the first term I'm going to distribute ar to r minus 1. I'm going to get ar squared minus ar plus br is something like plus b minus ar plus c equals 0. Okay, in this context, we're considering an equation where a, b, and c are constants that are given to us. Those are defined for this ODE. And now the question is, how do we find what value of r satisfies this equation? And just like before when we had constant coefficients, this equation is called the characteristic equation. And just like before when we had constant coefficients, this is also a quadratic equation. And the solutions to a quadratic equation are r equals, and the quadratic formula says negative b over 2a plus or minus the square root of the discriminant divided by 2a. But whenever we say like negative b over 2a, we're actually talking about the coefficient on the linear term in your quadratic. So this time it's not just b, but it's b minus a. And negative b would be a minus b then. You switch the order of subtraction for the minus sign. So I'm going to write r equals a minus b over 2a plus or minus the discriminant divided by 2a. And my discriminant is usually b squared minus 4ac. But this time it's going to be b minus a squared minus 4ac. And b minus a is the same thing as a minus b, only I like alphabetical order. So you can write it either way, it doesn't matter. But this is the formula that gives me the roots or the solutions to my characteristic equation. And therefore, that's going to tell me what these R values are for my solutions. I'm going to have a general solution that looks like some constant times t raised to the power r1 plus some constant times t raised to the power r2. Because this, again, with the plus or minus, is telling me about two different R values. One that gets the positive sign and one that gets the negative sign. And if my values of R are distinct from each other and they are both real numbers, then that's my solution. We can stop there because everything's a real number. Questions about that? Okay, so it looks really similar to the case with constant coefficients, but there's just these very subtle differences in both the form of the solution and how we find the R's. The next case is, well, what if R1 and R2 are not distinct real numbers, but what if they are complex conjugate values? In other words, what if my discriminant, which is b squared minus 4ac, what if the discriminant is a negative number? In this case, R1 is going to be some real part plus some imaginary part, and R2 is going to be some real part minus some imaginary part. And we can figure out what those would be because R is equal to a minus b over 2a plus or minus the square root of the discriminant over 2a. So that means my real parts are going to be a minus b over 2a. And my imaginary parts are going to be the square root of negative d over 2a. Because if my discriminant is negative, if lowercase d is negative, then negative d is actually a positive number, and you can take a square root of a positive number, and that's how you get the imaginary part here. Okay. But the question is this: if my general solution is c1 t to the power r1 plus c2 t to the power r2, this general solution has complex numbers that are not real. And the question is, how can we write this solution using only real numbers? And so what we have to do is recall some properties of exponents, like t raised to the r power is the same thing as e raised to the power natural log of t raised to the r power. And then that means this is the same thing as e raised to the power r times natural log of t. And then since we have this as our definition of R, a real part plus an imaginary part, we could write this as E raised to the power lambda plus or minus mu I times natural log of t. And I can distribute the natural log of t and then use another property of exponents that we like to rewrite this as e raised to the power of lambda times natural log of t times e raised to the power mu times I times natural log of t. E to the power lambda times natural log of t is the same thing as e to the power natural log of t raised to the power lambda. And then e to the power mu I natural log of t. This is where we're going to use Euler's formula. That really cool result. What is e to the power I theta? According to Euler. All right, you guys, I'll just go ahead and tell you because we got to move on. We got to cover some ground today in class. Euler's formula says e to the I theta is cosine theta plus I times sine theta. So that cosine is the real part of e to the I theta and sine is the imaginary part of e to the I theta. And that means whenever I see the next e over on the purple side of my page, where I have e to the power mu I natural log of t, that means mu natural log of t is like the theta in Euler's formula. And I can write instead cosine of mu natural log t plus I times sine of mu natural log of t. And if I want to keep track of both of my r's, I guess I should really keep track of this plus or minus sign right here. So like this is plus or minus mu I natural log of t, and then applying the Euler's formula, this is going to be plus or minus mu natural log of t and plus or minus mu natural log of t. So then e to the power natural log of t is what? T. So I can write t to the power lambda times, and do you remember what is cosine of negative mu natural log t? Cosine is an even function, and so it does not matter for cosine whether the argument is positive or negative. It doesn't matter, because if you have a negative argument, you get the same thing out of cosine as if you had a positive argument. Sine is an odd function, and that means making the argument negative would also just be the same as making the whole function negative. And so I will get plus or minus I times sine of mu natural log t. So we're getting close. I can write this finally as two separate terms because one of these solutions, like t to the r1, is going to have the solution t to the power lambda cosine mu natural log t plus sine mu natural log t. And then t to the power r2 is going to be the same thing as t to the power lambda times cosine mu natural log t minus sine mu natural log t. Sorry, I forgot my i's. Here's an I. Here's an I. So now what happens if I, again, look at some general solution where I've got a constant t to the power r1 plus a constant times t to the power r2? Well, throwing in this constant here and here, and then adding these together is going to make it so that I could I could rewrite this as y equals I'm trying to figure out what constant goes in front of the cosine. It would be k1 plus k2 t to the power lambda cosine of mu natural log of t. And then in front of the sine, what I would get is k1 minus k2 because of the negative sign when I distribute. And then don't forget your i's. And don't forget t to the lambda either. Sine of mu natural log t. Okay. Now, if k1 and k2 are complex conjugates, then k1 plus k2, that's going to have the same real parts on the k's, but opposite imaginary parts. And so if they have opposite sign on their imaginary parts, and I add them together, the imaginary parts are going to cancel. And so this definition of C1 is a real number. And C2 can be my constant K1 minus K2. And if these have the same real part, then subtracting them will get rid of the real part. But if they have opposite imaginary parts, then subtracting them is actually going to double the value of their imaginary part, right? And so this is a strictly imaginary number with no real part. Well, that's good because what I have here, what I'm about to underline, the k1 minus k2 times I, that would be c2 times I. And if I have an imaginary number times I, that would also make a real number. So to fix this, what I could do is define C2 as K1 minus K2 times I, and now C2 is a real number. There we go. So finally, the way that I can write my solution in a way that only involves real numbers is like this. And it should really remind you of the solution when we had constant coefficients. But there's little differences, like instead of e to the t, we have t to the power lambda. And instead of cosine of t, or cosine of mu t, we have cosine of mu times natural log of t. And sine of mu times natural log of t. But otherwise the same. Okay, so that's an important result for how to write a general solution with a negative discriminant with only real numbers. Finally, suppose that the general solution has only one value of r. That can happen if we have this formula for telling me what r is based on the ODE, and my ODE is going to look like this, right? If a, b, and c are such that a minus b over 2a plus or minus the square root of discriminant over 2a makes the discriminant equal to 0. We're saying, what if the discriminant is equal to 0? Well, then I would only have one value of r, because I'd be doing plus or minus 0. And r would just be the value a minus b over 2a. Then my general solution would become something like y equals a constant, c1, times t to the power r. But we know, since this is a second order ODE, that there should be another arbitrary constant times some other function right here, right? So how do we find the other part? And the process is called reduction of order. In reduction of order, we say, well, my first solution looked like t to the power r. And we're going to take a guess, and it's not so much of a guess as it is just a way forward. The way forward is to say my second solution is going to look like some function u of t times my first solution, t to the power r. And it might look like we're making a big assumption, but you know, this u of t can be any function of t, so maybe one of the factors in u of t is t to the power negative r, in which case you'd multiply t to the power negative r times t to the power r, and it would cancel out. And then, based on the other factors of your u function, you can have whatever function you want. So this is not even restrictive at all. It's not trying to take a guess or an ansatz. This is just some way to move forward with our solution. And then what we're going to do is we're going to take the derivatives, the first derivative and the second derivative of y2. So the first derivative, according to the product rule, is going to be u prime t to the r plus r u t to the r minus 1. And then the second derivative, according to the product rule, is going to be u double prime t to the r plus two ru prime t to the r minus 1 plus r times r minus 1 u t to the r minus 2. And then we plug these things into my ODE, which looks like this. Of course, we're plugging the y2 solution in. We'll see what we get. We're going to get a t squared times all of this stuff. So it's going to be, I'm going to go ahead and distribute. I'm not going to try to write this down a whole bunch of times. So I'm going to distribute. I'm going to distribute a t squared to each one of these terms in y double prime. So it's going to look like a u double prime times t to the r plus 2. And then the next term is going to be 2 a r t to the r plus 1 u prime. And then the third term over here, we've done that one and that one. Now we need to do the third term, which is going to be a r minus 1 t to the power r u. And that takes care of this, the first term in my ODE. So now we're moving on, and we're going to do the second term here. Plus b, I'm distributing the t to each term in the y prime solution, so it's going to be t to the r plus 1 u prime plus b r t to the r u, and that takes care of this term. And then the last little bit is c times y2, so it's plus c t to the r u. And this has to be equal to 0 for all values t. And the way forward is to collect the derivatives of u. So like we're going to make one term that has just u as a factor. And the u term on the left-hand side is going to be a times r minus 1 t to the r plus b r t to the r plus c t to the r times u. And this is going to be, well, let me factor out the t to the r as well. Might as well take out the t to the r factor. That's going to be the same thing as ar squared plus b minus ar plus c. And this is equal to 0, because that's my characteristic equation that we solved for r. So that's kind of cool. Get that one for free. And then what if we take this and we make just the u prime terms? The u primes together would give me 2ar t to the r plus 1 plus b t to the r plus 1 u prime. And this is going to be equal to 0 because r is equal to, oops, did I forget something? Where's my u primes? 2ar b t to the r 1 plus 1. So setting this equal to 0 would imply that r is equal to negative b over 2a. But that's not true because r is equal to a minus b over 2a. So that's not exactly true. Well, let's add then the u double prime term. Since that's something non-zero, let's add to that a t to the r plus 2 u double prime, and set that has to be equal to 0. That way, we collected just the u's, 1, 2, 3 terms from the u's, and that had to be 0. So that means everything else, the remaining 3 terms, with the u prime and the u double prime, that has to add to 0 as well. So this is actually just a first order differential equation. I know it looks like a second order differential equation, but if I say y is equal to u prime, then y prime would be equal to u double prime, and I can write this differential equation as 2ar plus b times y plus at y prime is equal to 0. Notice I also divided both sides by t to the r power. So if we assume that t is not 0, we can divide by t to the r. And then divide both sides by t to the r, and that's how I got rid of, divide by t to the r plus 1. And then we get this. So now we have a first order ODE, and I think it's separable as well. And since it's a separable ODE, I can subtract this from both sides and then divide both sides by y, and then divide both sides by at, and I would get negative 2ar minus b divided by at. And we'll take the antiderivative of both sides with respect to t. On the left side, the antiderivative of 1 over y is natural log of y. On the right side, the antiderivative of this is natural log of t plus a constant, and also times negative 2ar minus b over a. There's got to be a way to simplify that. Because if I've got negative 2ar plus b over a, and we say that r is equal to a minus b over 2a, substituting that in would give me negative 2a, a minus b over 2a plus b over a. So these 2a's cancel, and I get a minus b plus b over a. And minus b plus b is 0. A over a is 1, so that's a negative 1. Okay, so then this is going to say natural log of y is negative 1 times the natural log of t plus a constant. Take the exponential of both sides, and we get e to the power negative natural log of t, which is going to be t to the negative 1 power times the constant very good. And then what we are interested in is not y, but y was just a convenient change of variable. Because look over here, we said that y is equal to u prime. And so if y is equal to u prime, we say u prime is equal to c times t to the negative 1 power. What does that make u? What's the antiderivative of t to the negative 1 power? Yes, the antiderivative of t to the negative 1 power is a natural log of t. And that's what we wanted to find in the first place. I know it's been several minutes, so you already forgot what we were doing in the first place. But what we were trying to say is my second solution is going to look like a function u of t times t to the r power. And now we can say with confidence that this second solution is going to be u, which is an arbitrary constant times natural log of t times t to the r power. And I don't really need that arbitrary constant because I'm going to have one from right here anyways. And now we're finally ready to write my general solution. And the general solution to this whole thing is going to be c1 t to the r power plus c2 natural log of t times t to the r power. Oof. Okay. So that's how you write that's how you find and that's how you write the general solution to a homogeneous Cauchy-Euler equation. Of course, you don't have to do this every single time. You don't have to reproduce this every time you want to solve an ODE. So I'm giving you a handout that looks like this, and it summarizes what you're supposed to know. And your three cases are positive discriminant, two distinct real solutions, negative discriminant, two complex conjugate solutions, and discriminant equal to 0, you've got only one real solution, and you've got those three forms that your general solution to your ODE has to take. So you'll notice that like most second order linear homogeneous ODEs are actually not going to have elementary solutions, right? Like if you just put different coefficients that are different functions of t in front of your y double prime and your y prime and your y's, you're not going to get an elementary solution in like 99.99999% of cases. But at least between the constant coefficients and the Cauchy-Euler equations, we've seen some solutions to these ODEs that involve polynomials and exponents and logarithms and some trig functions, sine and cosine. But it's a zoo out there. There's way too many possibilities to talk about in one differential equations class. So here's exercise 4. Solve the ODE in IVP. Notice it's a Cauchy-Euler equation. And so the way you'd solve this is you would first write down your characteristic equation. And my characteristic equation for this is r squared minus 3r plus 2 equals 0. Only that's not it. That's not the right characteristic equation. That's what I would write if this had constant coefficients. I would write like a r squared plus br plus c equals 0. But the characteristic equation for a Cauchy-Euler equation is actually a r squared plus b minus a r plus c equals 0. And so what I really should be writing if I need my characteristic equation is r squared plus negative 3 minus 1 And now I can solve this quadratic equation like a quadratic equation. And I'd have to use the quadratic formula. It's going to be 2 plus or minus the square root of 8 over 2, which is like square root of 2, I think. I just realized I made a horrible mistake whenever I was making all of the example problems on your homework. Do you see what my mistake is? I try to have these r's be whole numbers, you know, and instead this is not a whole number. The problem is that I was giving these Cauchy-Euler equations coefficients that would make a nice characteristic equation if this were just b instead of b minus a. But now having to do the b minus a thing is actually going to mess up all of the solutions on the homework. You can obviously still find the solutions, they're not going to be nice whole numbers anymore. So I should probably go back and fix the homework and everything to make it a lot nicer. But anyways, this is going to give me two distinct real values of r. And so I can write our general solution as c1 t to the power 2 plus square root 2 plus c2 t to the power 2 minus square root 2. And that's the general solution to this ODE. What about the initial value problem? Notice for the initial value problems on this homework set, I'm not using 0 as my initial time, because if I were to use 0 as the initial time, then I would plug in t equals 0 and everything on the right-hand side would be 0. So you can't have an IVP with an initial time of 0 when we're dealing with Cauchy-Euler equations. It just doesn't behave nicely enough. Okay, so instead I'm using t equals 1 for my initial time. And that means I can set y0 equal to c1 plus c2, because 1 raised to any power is just 1. And then when I take the derivative of this, we find that y prime is equal to two plus square root 2 times c1 times t to the power 1 plus square root 2 plus 2 minus square root of 2 c2 t to the power 1 minus square root of 2. And plugging in my initial condition, which is that t should be equal to 1, and y prime is going to be equal to m0, then I get c1 times 2 plus square root of 2 plus c2 times 2 minus square root of 2. And this is my system of two equations and two unknown variables. I don't know what c1 and c2 are, but I have two equations to solve for them. This would be a whole lot nicer if these are just 2's instead of 2 plus square root 2 and 2 minus square root 2. So it's not going to be this bad whenever I fix the homework, but what we can do is take this equation minus 2 plus square root of 2 times this equation. And that way the C1s cancel. The C1s cancel out completely, and I am left with C2 times 2 minus square root of 2 minus 2 plus square root of 2 times C2. And so the 2's cancel because there's a positive 2 and there's a negative 2. And then there's negative 2 square root 2 C2 left over. Same thing on the left side. And then I can solve for C2. And C2 is going to be equal to M0 minus 2 plus square root of 2 Y0 divided by negative 2 square root of 2. And knowing C2, I can calculate C1 because C1 is just Y0 minus C2. And so having calculated C2 first, now I can calculate C1. Okay. Questions about how to solve this? That's the easy example. Let's see what the next one says. And like, man, I might just go ahead and change these coefficients because like I said, it's not nice working with numbers that aren't whole numbers. So like in this one, I need the characteristic equation to be AR squared plus B minus AR plus C equal to 0. And that would give me R squared plus negative 2 minus 1, which is negative 3R plus 2 equals 0. That one actually does work out really nicely, doesn't it? It would work out to be R equals positive 1 and positive 2. But I had intended this example originally to be my example where I have two complex conjugate solutions. Because if this was a negative 2 instead of a negative 3, then would that give you two complex conjugates, or would that just give you one real? Let me think about that. If there's negative 2, it would be 4 minus 4 times 8. It would give you negative 4. It would give you plus or minus I as your solutions.
Can't you just factor it? So it'd be R minus 2 and then R minus 1 as your two factors. So then R would just equal 1 and 2.
You're right. Yeah, you're right. What I'm trying to do is I'm trying to make this so that instead of a negative 2, this should be minus 1. Let's make that a minus 1 and see what happens. So if this is a minus 1, then this becomes negative 2, and now what are my values of R? My discriminant is going to be negative 2 squared minus 4 times 2, which is 4 minus 8, negative 4. There we go. Okay, so I wanted to have complex conjugates for R so that we could work one of these examples together. And so the real part of R is lambda, which is 1. The imaginary part of R is mu, which is 1. So this is going to be a relatively easy solution. I have to write my general solution as C1 t to the power lambda cosine of mu natural log t. plus c2 t to the power lambda sine of mu natural log t. Lambda is 1 and mu is 1, so that means I have c1t cosine of natural log t plus c2t sine of natural log t. Now let's worry about the initial value problem. In the initial value problem, I'm going to have to eventually take this derivative, so let's just go ahead and do it. In the derivative, I'm going to have c1 cosine natural log t plus I'm thinking derivative product rule on this first term. I already took the derivative of t, now I have to take the derivative of cosine. So it's going to be c1t times negative sine of natural log t times the derivative of the inside function. So times 1 over t, right? Derivative of natural log is 1 over t. And this 1 over t is going to cancel with this t. And so I'm not going to have to worry about that. Those will cancel each other out. And so when I'm writing this down, I'm going to write c1 times negative sine of natural log t. Okay, the next term is going to have derivative c2 sine of natural log t. And then the derivative product rule says I also have to take the derivative of the sine part. And that's going to be c2 times t times cosine of natural log t times the derivative of natural log. And this 1 over t and this t are going to cancel out so that I get c2 cosine of natural log t. And for the initial value problem, we are going to say t is equal to 1 because of these ones. And then if t is equal to 1, y0 is going to be c1 times 1 times cosine of, what's natural log of 1? 0. Natural log of 1 is 0. So this is cosine of 0. And then this is c2 times 1 times sine of 0. What is cosine of 0? 1. What is sine of 0? 0. So that means c1 is equal to y0. Moving on to the derivative. For the initial value, we say m0 is equal to c1. What's cosine of natural log of 1? 1. What's sine of natural log of 1? 0. So m0 is equal to c1 plus c2, and that would imply that c2 is equal to m0 minus y0. That wasn't so bad. Of course, the initial value problem might be a little bit more complicated if you didn't have 1 and 1 for your real part and your imaginary part. If this was like 2 and 3, then of course there's going to be a little bit more algebra when you get to this point. But keeping t equals 1 in the initial value problem is nice because the natural log of 1 is 0, and cosine of 0 and sine of 0 are nice numbers. So we'll try to do that with our initial value problems. All right, one more example. This is another one where I'm going to have to change the coefficients so that it behaves nicely. But in the first place, before I do anything with this ODE, I'm going to divide it by 11. because I see that everything is divisible by 11. So let's just go ahead and take out that greatest common factor. And what I really wanted to demonstrate with this example was that there's cases where the discriminant is equal to 0. Unfortunately, we're going to miss the mark here because the characteristic equation is r squared minus, and then it's b minus a, right? So it's negative 10 minus 1. It should be minus 11 r plus 25 equals 0. And I need this to be negative 10 so that I can have a repeated root. So really what I wanted was to have this be negative 9, and this could be negative 10, and that means this number should have been negative 9 times 11, which would be negative 99. There we go. And having done that, we can finally solve my problem. How does this factor? R minus 5 squared. So that means I have only one value of r repeated. What does the general solution look like then?
C1 t to the r t to the fifth, yeah. Plus C2 t to the fifth ln of t.
Nice. So then let's rapid fire and get this IVP over with. In my IVP, t is equal to 1. And, oh, I also have to take a derivative of my solution. So y prime would be 5 c1 t to the fourth. And this is going to be product rule. 5 c2 t to the fourth natural log t plus c2 times t to the fifth times the derivative of natural log that derivative of natural log is 1 over t, cancels out one of the t's. And then we apply initial values. So this would tell me y0, when I plug in t is equal to 1, is going to be c1 plus c2 times 1 times natural log of 1. But natural log of 1 is 0. This is telling me that at the initial value, I've got 5 times c1 times 1 plus 5 times c2 times 1 times natural log of 1, which is 0, plus c2 times 1. That tells me that c2 must be m0 minus 5y0.